Good morning, mathematicians. How are we all doing today? Whoa! I haven't even seen that background yet. Fantastic stuff. Yeah. Yeah, we had a long discussion yesterday, and cool stuff got talked about. What is this? Looks like an interesting video. I'm seeing a lot of other small math content creators, which is great. Love to see it. Yesterday, but they all have video production quality that's way better than me, which is also fine. I'm not. One of these days, I'm gonna get things looking good around this channel. But I like just chatting with you guys. Good morning, Edit Smith. You're so on the ball. You got A+ for attendance. Yeah. So, I mean, okay, there's probably people who are going to show up from yesterday. So I don't know if I should start talking about stuff from yesterday yet. 49 seconds, nice. New record. Yeah. I gotta make it harder for you guys. I gotta become less predictable. Man of mystery. Actually, what I probably should do is just, become more predictable, so that people know what time they can catch me. But I don't know. I don't like the one of the beautiful things about grad school is that, well, there's like, I guess, a lot of pressure, and you have to work a lot in one sense. On like, you're also very much control of your time, which is a double-edged sword. So if you're not someone who's like, I mean, even if you're someone who really needs a strict schedule to stick to, then it can still be fine. Like, but you also need to like create that schedule and hold yourself to it. Or maybe you have a supervisor that's like, I need these results by this week or something. But for me, I like being loosey-goosey, and I wonder, I don't know, maybe I would be better if I wasn't as loosey-goosey. I don't know, but I'll be honest with you, I really like being loosey-goosey. I like my time being my own. That's why I didn't even want to commit to like, oh, I'm gonna do this every morning. It kind of seems like it's shaking out that way now that I've made it a bit of a habit. I think I might just stream every morning except for Thursdays until I don't have to be up early Thursdays. Then I can just stream every day. But yeah, even then, I really like being in control of my time, and that won't stay forever. I was looking for this post. This post is great. What was your favorite open problem and why? Yeah. Rendezvous problem. Two players start at unknown locations in a given space and must find each other as quickly as possible without prior communication. Oh, you have a big YouTube addiction, and I go on right after your first class. Well, great. Let me just parasocially take advantage of your addiction. Ha ha ha. Ha ha ha. Fantastic. You're probably generating several pennies of revenue for me with each view, so it is appreciated. No, but actually, I appreciate you just being here, whether it's driven by a deep addiction or love of mathematics. Yeah. Anyway, funny little joke here at the end of this post about the rendezvous problem. I didn't know about the rendezvous problem. That's fun. This is a good one, I think, because it's one that you could just like, have people write stuff down and, and there's a continuous version of the problem. Yeah. Mutual search problem in a telephone network space. Oh, that's part of the same problem. Ah, interesting. Okay, so applied. Oh, there's another. I mean, okay, I was ranting last time about all of the things that my crazy numerology about graph theory, but there's one conjecture I was thinking of. It's Iridish. Oh, I do not know how to spell this as a guy's name. Giarfras, something like that. Giarfras conjecture, which asks, does every three regular graph contain a 2 to the n cycle? So a cycle whose length is a power of 2. Open problem. This has been, I think they posed it around like 94 or something, and it's unsolved. I have some very, very loose thoughts on this that probably don't mean anything. But, well, first off, three regular graph has to have an even number of vertices. Sorry, an even number of... Let's see. What is it now? So the number of edges is 3 times the vertices divided by 2. Right, so that's the number of edges. Right, yeah, so the number of vertices has to be even, because then that implies that v is 2 times m over 3. So that has to be an integer, and this can only be an integer if m is divisible by 3, right? These two aren't gonna, like, yeah. So, yeah. What else was I going to say? Oh, yeah. So the other thing I thought about is it turns out that if you look at all of the subsets of a graph, all the subsets of its set of edges, this forms an F2 vector space. Actually, you don't even need to say something so fancy. It's just... you have a binary operation on these, which is just given by the symmetric difference. And it turns out that so there's a subspace of this, or like a subset that's closed under this, which is generated such that A determines the edges of an Eulerian subgraph. And so that subspace of Eulerian subgraphs is closed under this operation, and it's called cycle space. And what's really interesting to me is that for cubic graphs, so normally cycle space is actually just generated by Eulerian subgraphs in general. But for a cubic graph, cycle space is actually going to be everything in it will either be an honest-to-God cycle or a disjoint union of cycles. So it just makes me wonder if there's some way to argue this using cycle space. Also, there's like little hints of 2 to the power of n stuff floating around, because viewed as an F2, well, okay, we don't even need to do the F2 vector space nonsense. We could just think about it because it's a collection of sets of a power set. But the number of cycle space of elements in cycle space itself is 2 to the power of some number, and any subspace of cycle space should have a number of elements equal to 2 to some power. And then also there's this sort of parity thing going on, right? If you're in the symmetric difference, right, an edge will only appear in the symmetric difference if it's in exactly one of A or B, but not both. Okay, so there's no real math here. I don't have anything here, but well, I've tried to do more legitimate things here. Play around with these little ideas and whatnot. But it does make me wonder if there's some way to exploit cycle space to prove this. What else we got going on? Is that like algebraic graph theory? What's the prerequisites for it? No, I'd say it's just ordinary graph theory. Sorry, I mean the cycle space. Sorry, right. The cycle space, I guess you would call algebraic graph theory. Yeah, you can look it up in Godsill Royal. Which is a book on algebraic graph theory. Yeah. Forget about the F2 vector space stuff if you want. If it's easier, just think about the fact that you have symmetric difference on subsets of edges. Also, it'd probably be helpful if I gave an example. So let's look at this graph. Right? So what are the Eulerian subgraphs? So I'll draw it like we formalize it as sets of edges, but I'm just going to draw it in terms of graphs. So we always include the empty graph. We have the one that's just a cycle on the one side. We have one that's just a cycle on the other side. Shouldn't it be A union B, not C? Wait, what did I write? Oh my God. Thank you. Thank you for pointing that out. Yeah, I also wish YouTube comments accepted LaTeX formatting. Wow, that would be, I wonder, there's got to be a way to make that work though. I mean, there's Discord servers have LaTeX formatting. I wonder if there's a way, if I could just have like set up a Discord server and have chat like type things in there if they want, and then just monitor that during streams as well, or instead. I thought about that before, but also I don't want to have to moderate a Discord server. That sounds awful. I mean, probably it would be fine now, but like if this channel got a lot bigger, I don't have to worry about moderators. But maybe I should just stop being a little baby and do it. Well, yeah, some custom formatted chat box. I mean, come on, there's got to be. I got to be able to find some computer science nerds in my audience that can rig it up for me. Sick, yeah, that'd be great. Yeah, take a look. It'd be sick to get something like that going. Yeah, so these are all the Eulerian subgraphs on the. I'm just trying to separate them out here. So, for example, if you took the symmetric difference of this one and the symmetric difference of this one, you would get this one, right? Because like most of the edges only appear in exactly one of these two graphs, so they'll appear in the final thing. The only one that doesn't is this middle edge, right? And it appears in each of them once. And also the empty set acts as the additive identity. So the symmetric difference of any set is just, you get that set back, for example. Yeah. I mean, this was an example of a graph where all of the circuits were cycles. Hey, Nicole. I'm gonna jump back over to here. I mean, that's fine. I feel like I mean, okay. It's funny for me to be like math. Like, what's your favorite open problem? Like, PMP is probably one of the most like important of the Millennium Prize problems. But I feel it's like like the iceberg, like the mathematical iceberg. It's like if I'm gonna be a real hipster snob about math, it's like, oh, that's the vanilla like entry point. Yeah, like, oh yeah, everyone loves the Riemann hypothesis or something. It's like, yeah, I want something. Yeah, give me something deeper. Give me something more obscure. What is the cycle space of a graph with two disjoint cycles? Um, yeah, used symmetric difference operation in sets and related them with a property in groups. Yeah, yeah. Given any set, actually, given any set, if you look at the power set and the symmetric difference, like this forms a group. And in fact, if x is finite, then this will just be isomorphic to a bunch of copies of Z mod 2 to the power of x. And so that's actually okay for those of you who aren't confused by the F2 vector space stuff. Like that's where we get the F2, or I mean Z mod 2 vector space structure, which is it's a little bit stupid because you just have one scalar, but so I don't know. It's maybe better to think of it as a group or Boolean algebra, but I like thinking about it as a vector space, because then there's also questions about for graphs. There's questions about like cycle bases. So like there's a theorem that says you can always find a basis for cycle space, which consists of cycles. And I think there's even like open problems around like efficient algorithms for that. I don't know what their applications are, but yeah, there's interesting questions there. So awesome. Well, Nicole, if you got more fun facts about the symmetric difference thing, you gotta drop them in chat. The group would be isomorphic to XOR acting on a binary array of constant length. Yeah, absolutely. I mean, you can sort of see that as being like choosing a basis for the vector space. It boggled my mind to calculate cohomology groups with coefficients in PG. With coefficients in PG? Coefficients in PG. I'm not sure what that means, but I guess I gotta look that up. In the power set of G. So you computed, maybe I'm misunderstanding, but you computed like group cohomology with coefficients in the power set of G. I've never heard of that. Let me know where I can read more about that. That sounds interesting. Okay, so actually, wow, two related cohomology questions just popped up. Can I talk about étale cohomology and its relation to other types of cohomology? A little bit. I'm not a pro, but I'll try in a moment. But I think the other question maybe I should answer first is, what's cohomology and why is torsion-free cohomology ring so special in differential geometry? So I don't know why torsion-free cohomology is so special in differential geometry. That I can't help you with. But what I can say a few words on is, what is cohomology? And people might get mad at me for saying this, but here's my like absolute low level, complete beginner description of cohomology. So or just regular homology, measures the failure of a map to be surjective. I'm not wrong. Okay, I'm not wrong. So any of you homological algebraists who are, might be freaking out in the chat, being like, "What the hell is he talking about?" I stand by this as the simplest one-line description of what cohomology theories are. I stand by this. But, okay, there's a lot more. There's a lot of depth here. So let's look at, for example, a very, very basic example, like the rank nullity theorem. Rank nullity theorem, right? It basically says, oh God, I always say things wrong. I think in exact sequences now, so I don't know what the actual rank nullity theorem is supposed to say. But here's one way to say it. Suppose that you have this map from U to V is injective, and suppose that this map from V to W is surjective. Then the dimension of V is equal to the dimension of U. Oh, and actually, there is one important thing. Well, specifically, this needs to be the kernel of the map from V to W. Then the dimension of V is the dimension of U plus the dimension of W. So yes, it is. Yes, it is based on the intuition for the image kernel definition of exact sequences. Yes, I mean, that's exactly what cohomology is measuring, right? So like, let's look at, right? So a sequence is a complex if the image of one map is contained in the next. So if the image of F is contained in the kernel of G, and all the cohomology is so we say it's exact. We say it's exact at V if this is an equality, and if it's inexact, well, even if it is exact, one thing we can do is we can study the quotient of the kernel modulo the image, since the image lives inside here. And then this is what I mean. It's so cohomology is the study of the failure of F to surject onto the kernel of G, and so this is basically the cohomology at V, and that's the basic idea. But then, okay, so we have like, that's the basic like algebraic idea of cohomology. But I mean, it gets so much more sophisticated, right? Because you've probably seen, some people might be confused because you've probably seen something about like, oh, but isn't homology something about spaces? Like, I thought like the homology of the sphere, this is supposed to be Z in degree 0, and 0 in degree 1, and Z in degree 2, and then 0 in all the higher degrees, right? So it's somehow measuring the degrees of the holes. It's somehow measuring holes in topological spaces. Yes, so that is one application of homology, which in that context of algebraic topology. And what one does is basically the way that you get this, but the connection from the topological definition of homology and the more general algebraic one is basically for every topological space, you create a sequence of vector spaces of continuous functions. And then you basically look, and then the homology of your topological space is defined to be the homology of this sequence. So that's a basic idea. Let me just catch up to some of the stuff that's going on in chat here. Paper called Ends of Groups and the Associated First Cohomology Group. Okay, let me just stick that in another tab for later. Ends of groups and the first cohomology group. Studied topological methods and group theory by Scott. Okay. Well, I'll just yeah, at least I've got this. Okay, that's probably the paper there. Nice. Okay, yeah, I'm going to take a look at this later. That seems cool. Jean Leray. Yeah. Jean Leray, the GOAT. Hi, Jens. What was the most general set conditions for a space to uphold rank nullity? Well... I mean, rank nullity is really a theorem about, it's a very algebraic thing. It's not really a set thing, I would say. I mean, maybe there's other things you could say about rank nullity stuff, but okay, one answer is modules over a PID, because that's basically the class of rings that behave most like vector spaces in general, and things just get more complicated from that. Yeah, nice. I just saw the comment in chat right after. Yeah, exactly. Your professor asked you to study embeddings of a n-dimensional manifold on the boundary of m-dimensional manifold where m is bigger than n, and he said for it to be smooth embedding, look at its cohomology rings. Yeah, I don't know. I'm not familiar with that idea, unfortunately. But there was another question back a little bit about talking about étale cohomology and its relation to other types of cohomology. Yeah. So I mean, we've gotten very there's much more general sort of cohomology theories these days, and well, étale cohomology is maybe a little bit more complicated because now we're working with étale sheaves. Oh, which way is a fleck go? I never remember. So like, well, I should say, okay. So I said up here that like cohomology is about the failure of surjectivity of maps, right? And so, well, we need some notion of kernels, and we need some notion of images, and we want to be able to like generally guarantee that I can like take quotients of stuff. So, I mean, there's more to it than that, but the general setting, that we want then is what's called an abelian category. So the classical example is a category of abelian, is the category of abelian groups. But basically, like, okay, there's more precise technical definitions, but the point of an abelian category is that like you have you have sort of all the nice things. You have kernels and quotients and things that you need to make cohomology theories work. And it turns out that the category of sheaves on a topological space, or better yet, you know, if we're going to talk about étale sheaves, we want to be thinking about like locally ringed spaces, like algebraic varieties or schemes or something. This happens to be an abelian category. I am using OBS. Yeah. If anyone has recommendations for something better, this seems to be working fine for me already. But does rank? No, I don't know if rank nullity because I don't know if rank nullity holds for an arbitrary abelian category, because like you need some notion of dimension, right? And in an arbitrary abelian category, you're just not going to have a notion of dimension necessarily, right? So that's why I and Nicole mentioned modules over PID, because modules over a PID still have like a good notion. I mean, there's more general kinds of modules that still have a good notion of dimension. Modules in general do not have a good notion of dimension. Even if you believe in the axiom of choice, you will have modules with no well-defined basis. So you can find two bases of distinctly different cardinalities. But in the world of modules, it's like you ask yourself all the things you like can do in linear algebra, like how far can you push that to the general world of modules? And the thing is, modules over a PID is where you can push it to. And so and so we still do have like modules over a PID still have a good notion of dimension, and it's still pretty well behaved, and so rank nullity should definitely hold there. I'm not saying that it can't hold in other contexts over a module, but it's just once you leave the world of PIDs, things aren't as nice. They're less guaranteed. So yeah, and there's a really cool homological algebra classification of like how far you are from a field or a PID in terms of the lengths of the minimal projective resolutions you can find, which is so cool. I love it. But so getting back to so we have abelian categories. We have the category of sheaves on topological space or a scheme or a manifold, something like that. That's an abelian category, and so we can do cohomology theory with it. And so I mean, we have theorems for, so this isn't étale sheaves yet, but like there's theorems that say that you recover the ordinary cohomology. So I think I could be stating some of this wrong, but it's something like, if you look at, say, what is this, like singular, maybe singular, there's some theorem to the effect of this, that like if you have a singular, the singular homology of a topological space with z coefficients, then that should be isomorphic to the sheaf cohomology with values in the constant sheaf on the space, the constant sheaf determined by z on the space. So there's something like that. I could have the exact, again, maybe we need some qualifying words here, and maybe there's some other condition, but there's theorems that are effectively like this, for example. So if the category is additive, then it holds. No, I don't think so, right? Because additive is like part of the assumption of being abelian, right? And yeah, so I don't think additivity. You're not necessarily don't have a good notion of dimension. There could be other things though that have rank nullity vibes that get preserved. I don't know, but. Well, glad you got to catch one of these lives there, Nerd Coke. Can I also talk about how one obtains representations of Galois group from étale cohomology? Sort of. Yeah. Give me a second. Let me at least finish this thought here on étale cohomology. Talking about sheaves in algebraic geometry. Have I looked at motivic homotopy theory? No. Not at all. I'm vaguely aware that it exists. The word motivic, like any good mathematics, both scares and excites me because it's all over the place. There's actually, so recently Julia Gordon came to visit Calgary for a few days, and she gave a talk to research group, and we discuss some things. And she does a bunch of stuff with something called motivic integration. But actually, we didn't end up talking about that. We ended up talking more about like nilpotent orbit stuff and Kryllov's orbit method. But yeah, and I mean, secretly, like the big idea in Langlands is like eventually, you know, somehow we want to be talking about some category of motives and L functions there, but that's a little bit beyond me. But yeah, it's something I'd like to know more about. But you know, so only so many hours in the day, and now I spend at least one of those streaming. But so I mean, there's also the category like of étal sheaves, right? Étal sheaves. I mean, this is a more fancy version of sheaves because now we have this is sheaves on a, you know, we have a, instead of the ordinary topology, we deal with a Grothendieck topology, and we have what's called a site. But it's just sort of like a generalization of how open sets on a topological space work to a more general category. And sheaves in this sense also form the so this and that. I mean, specifically the Grothendieck topology is called the étal topology, and let me look up which way the Fleck goes. I won't remember 5 minutes from now, but it does go to the right. Okay. Don't wanna upset all my my French followers that might be in chat. And so the rank of an elliptic curve is a motivic measure. Yeah, I have no idea what that means, but I'd like to understand it one day. So yeah, the particular topology we use here is called the étal topology. So again, we get some abelian category of étal sheaves, and so we can do a cohomology theory there. And in that case, though, there's actually a way to write it in terms of like some limit. You end up being able to write it as some limit of sheaves, because basically, like an étal sheaf, this is all sort of done in terms of having like a family of covers of your topological space, and so your étal sheaves really are some like system of sheaves, and then you can take like the categorical limit of, I think, more usual cohomology, but now I'm getting into stuff that I'm not super well versed in, at least not well enough to just bust out on the fly without saying a lot of incorrect things and a lot of lies. So that's the basic idea between étal cohomology. Can I talk about how one obtains Galois representations from étal cohomology? I mean, a little bit. I can say in detail a more related or a similarly related thing. So, I mean, if you have, so here's just like a basic idea. Suppose you have some Galois group acting on an algebraic variety, right? Like say that gamma, so say that X is a variety over K, and maybe let gamma be the Galois group of K bar over K. So then it will naturally act on the variety, right? Because you're fixing the K points. So this action, of course, induces, right? So that means that every G in gamma gives you a map on the variety, and so of course that induces a map on cohomology, right? And now your cohomology groups are vector spaces, and so, well, what do you have? You have some linear map on vector spaces that respects composition, and so therefore we have a representation of your Galois group on cohomology. Okay, it's a little more complicated than this because, I mean, Ital cohomology is like a little more complicated. But you hope I can create a guide for algebraic geometry for undergrad students on YouTube. Some like algebraic geometry prerequisites. Well, I think there's already a lot out there, to be honest. So there's a lot out there on algebraic geometry. So I don't feel like at the moment I have that much to contribute that I really want to like put the time in, because I already feel like there's so many great resources out there. So maybe I'll just mention a couple things. I think Karen Smith has a book for algebraic geometry for undergrads. First off, I would just Google, like, there's a whole bunch of like very popular Math Exchange posts where people have asked what the prerequisites they need for algebraic geometry are. So just go look at those. But also, you know, sometimes people say more prerequisites than you need. I mean, you don't need a perfect understanding of everything to get started. So just crack open a book and like pick up things as you go. You know, the book of elliptic curves by Silverman has a great. I think the first chapter is a great introduction to varieties, in the sense that it's maybe not the best place to learn it if you've never been exposed to it before, but I think it gives you some like great motivation in context, and it has references. So it would serve as a good sort of starting point to work from, and then go off and find like these other references. But yeah, there's also invitation. Yeah. Smith's invitation to algebraic geometry. Yeah, definitely. Yeah, very friendly. Also, I mean, okay, this is not it's not as friendly because it's more abstract, but of course, Vakil's notes, who actually Ravi Vakil. There's a really nice looking print version finally available. I think I'm gonna buy myself a copy because it looks really nice and it's awesome. And there's also, though, you can find, I think it's called the Agitalk lectures, algebraic geometry in the time of COVID. Those are all on YouTube still, I'm pretty sure. And so that's a great thing to follow along with. I mean, yeah, for grad school, you'll need more fancy things, but just like, don't, like, you need to start somewhere, right? So just don't like, I don't know, don't worry about if you're doing this advanced enough or not. Like, you just need to start somewhere. You need to dig in somewhere. And so, hey, maybe if you start reading Karen Smith's book, you're like, oh, this is too easy. This is for babies. I'm a genius, and you can go read fancier things and go read fancier other books. Go read Ravi Vakil's book or something. Actually, I think you should read more than one book. Like, you should have more than one book open. One book should be your main thing, and then you should have at least one other book to help you explore deeper things faster. But just like, I don't know, work on what you can understand. And so start with Smith's book and just get an idea of what's going on. Cut your teeth, do some actual exercises, and just worry about that other stuff later. I think it's better to worry about building a strong foundation first. You know, like, I know it's tempting because other people around you might be talking about very fancy stuff like Ital cohomology, and yeah, Smith mentions this other book here. Yeah, I haven't looked at that one either. But there's so many books out there. There's so many discussion posts on algebraic geometry, the way to do it. But yeah, just don't get too intimidated or distracted by people talking about fancy things around you. I mean, it's good. Still go explore those. Still, like, right click tab, late night Wikipedia and lab blue links and green links and like learn what's out there, but get those basics down, because like I've definitely met some people who are bright, very bright, but they spend their time reading about all these very fancy things, and they can they can recite some words about bundles of gerbs and blah blah blah, but then they don't know they struggle to prove like a basic thing about rings. You know what I mean? So and I also say this as someone that in certain areas I'm guilty of this, and there's certain things that I do wish I just had a stronger foundation in the basics, and I think will make it easier to learn things later on. You'll start grad school this summer with a concentration in algebraic topology and differential geometry. Well, then don't worry about algebraic geometry. Don't worry so much about algebraic geometry. Category theory is a must for algebraic topology, certainly, in the modern era. Depends who you're working with and what your focus is, but 99% of everything is category theory now. So yeah, I don't know. If you're starting this summer, it's not like you're going to make deep advances in the next few months, but you can do more to prepare yourself, just find some differential geometry and algebraic topology. If you're doing differential geometry, like Bot N2 is a great book, right? I was recommending that one before. It's called what is it? It's called Differential Forms in Algebraic Topology. So it's the intersection of differential geometry and algebraic topology. Go read that book. Go learn as much as you can from that book. I would say that'd be a good use of your time. And look, in grad school, you're gonna be taking courses which are gonna get you caught up. Your supervisor will have a particular project in mind, and so they will guide you towards the things you need to understand in order to do that project. Am I familiar with Klein's lectures on the icosahedron? His obsession with the icosahedron and its relation to the quintic is what led him to the quartic. Yes, I am. I haven't read that book carefully, but I am aware of it, and I am aware that there's these cool things going on between the icosahedron and solving quintic polynomials. So of course, famously, there is no general solution to the quintic. This is a famous result from Galois theory. No solution by radicals, but there's still these sort of transcendental solutions and all this stuff you can, and somehow it relates to the icosahedron. You take a icosahedron on the Riemann sphere and you put poles at the vertices, and I don't know. You do some crazy stuff there, and something bring radical. But yeah, I'm vaguely aware of this stuff. And it seems really cool. Okay, I'm gonna go right away, but let me just finish up one thought here. Going back to ital cohomology. I don't know if the person who originally asked about explaining ital cohomology is still in the stream. Armin. But here's one cool example that I think, so you don't even need ital cohomology for this, but I think you can rewrite it in these terms. So take an elliptic curve over the rational numbers, and it gets acted on by the absolute Galois group. And the points, so take a prime, or let's take a prime L, and sweet, you're here. Okay, great. So then you can appreciate this. Then which way does the map go now? I guess it goes this way. So you have a map. So this is these are all the points on the elliptic curve of order L to the n plus 1. So that means if you add a point, remember elliptic curve has a group law, if you add a point to itself L to the n plus 1 times, oh, don't worry about barging in with anxiety. That's what these streams are all about. If you add it to itself n times, you get the identity, which we often write as L, right? So if you had a point that was L to the n, and you multiply it by itself at L times, this new point will have order L to the n, because you're just multiplying this point by itself L to the n times, which is just multiplying the original point by itself L to the n plus 1 times. And it turns out that these groups are just isomorphic to two copies of L to that power. So in other words, we get a map from L to the n plus 1 cross Z mod L n to the n plus 1 times itself to Z mod Ln cross Z mod Ln. And then, but the Galois group also acts on each of these individual spaces in a way that's compatible with this map. So this diagram commutes. So we have the Galois group acting on all of these spaces in a way that's compatible with this map. And so if you take the inverse limit of this system, well, what you get, the inverse limit of this is just the L-adic integers. And so, in other words, we end up getting a representation of the absolute Galois group on the L-adic integers. So we can view this as a representation, like a homomorphism from our absolute Galois group into GL2 valued in the L-adic integers. Well, technically, to be a representation, you need to vector space. So whatever, you just tensor this up with Q, and you get and it's GL2 in QL. So that is one way that we get Galois representations out of elliptic curves. But yeah, this is part of a whole general process of getting Galois representations from curves using italical homology. And this is all part of Langland's, actually. So remember, Langland says that automorphic reps match up to Galois reps. But you might have heard that Andrew Wiles, so he proved a very special case of Langland. So he said, well, there's also a bridge from modular forms to elliptic curves. And, well, I just showed you how each elliptic curves gives you a Galois representation. There's also a way in which each modular form gives you an automorphic representation. And somehow this bridge is all compatible. So this is the modularity theorem here. Currently reading a book on elliptic curves, and he has a chapter on the icosahedron. Wow, so much cool stuff to look up. Oh, McKean's book on elliptic curves? Crazy. McKean, elliptic curves. This one? Henry McKean and Victor Moll? Let's see. Icosahedron. Ooh, theta functions, right. I could see, because I know that theta functions have something to do with, also have something to do with the icosahedron. So it makes sense it would be in here. Oh, icosahedron and the quintic. Cool. Well, I'm also going to check this out. Yeah. Anyways, I'm going to check that out later, because I got some work to do. I got some theorems to prove. I got some groceries to get. I got a leg day to hit. Begin to have an interest in commutative algebra. Find that most theorems in Matsumura's book assume Noetherian. Is this going to be wasting my time if I want to pursue number theory? No, I don't think so. I think a lot of rings that you work with in number theory and algebraic geometry are Noetherian. We like our Noetherian rings. They're nice. So no, yeah, you're definitely not missing out on a lot. Assuming Noetherian, that's an important condition. But you should probably, with that in mind, be aware of which things are essential about Noetherianism. I mean, non-Noetherian rings still exist and they still matter, but yeah, I don't. That's not. Yeah, that's not any huge restriction for number theorists. You're definitely going to be dealing with Noetherian rings a lot, so absolutely no worries there. Okay, ending the stream for real now.